particular lecture, we're gonna analyze the following problem. So I set up a, a table fan or a stand fan at a certain location in my lab, something like this. This is the top view, and I marked out various positions on the floor. Each of the positions were separated by 1 feet. So distance between each cross is 1 feet. And what I did was I took a vein anemometer. Or a fan anemometer. I don't know. I mean, you can call it whatever you want, but basically it's a device like this. It has a housing like this, and it has a fan like this. And when wind blows like this, the fan starts to rotate, and the microcontroller inside is able to transduce the RPM of the fan to the wind speed. Okay, so the fan is turned on, and then I stand at various positions in the hallway, and I denote this position where the fan doesn't rotate at all as 0, 0. So this distance is also 1 foot, and so we'll call this as the origin. I mean, we don't mind. We can call this as the origin, and we have a bunch of points. So I went ahead and collected data for all these kind of marked locations. Okay, so what do you expect? I mean, first things first, we expect the fan to draw air like this and push it out. So because a typical fan has a casing like this, and this point is closed. Okay, so something like this. So immediate to the vicinity there will be, I mean, of course there will be a velocity, but it will not be high. At some distance it will be high, and then it will be something like this. So at some location we expect a maximum velocity, and if I look at the velocity field at this transect, I should have a variation of velocity like this. Okay, and along the actual location as well, I should maybe have something like this. Well, let's see whether we are able to achieve all these kind of variations, and let us try to reconstruct the two-dimensional image of this entire problem. So let's begin, and just to give you some context, all the data files are saved like this. So D02, so I saved the data files with this particular name. So D02 means the row number is 0 and the column number is 2. So the row number actually corresponds to a Y location, and the column number corresponds to X location. Okay, so we have all these kind of data sets. So let's start processing the data. Let me create a new file. Let me select Python 3 as the interpreter, and we're gonna need this is the standard thing. We've been importing it, but in this particular problem, additionally we're gonna require a data frame. So we're gonna import pandas. So pandas is a module with which we can do data analytics, but in this particular example we're just gonna use pandas for loading the data, and because the data is actually a CSV file, so let me open a data file and show you. So this is how the data file looks like. So it stores the date and time, it stores the temperature in degrees Celsius, it stores the velocity in meters per second, and it tells the name of the instrument, it Testo 410i. So the name of the brand is Testo, and they manufacture such kinds of things. And the serial number of the device is 49005051, and the device is courtesy of the refrigeration lab. Professor Saurav Mitra is the person whom I borrowed it from the mechanical engineering department. And we use this routinely in many of our experiments to measure wind speed. So I'm going to import pandas, and the utility of pandas is primarily to um, just to help us import CSV files, right? So let me do this. So data frame equal to pd.csv. Okay, pd.read csv, and here we will give a file name. So let's say d2 comma 2. So let's run this and let's see what df actually contains. So df is actually this entire data. It's this table. Okay, so what can we do with this table? I mean, we can't really do anything with this table, but what we can do is sort of isolate the different columns from this. Okay, so df um, this will give us the velocities, and actually once we have this, we can do np.mean to obtain the mean velocity. So this gives us a clue on how to go about it. So let me sorry let me do that. Let me cut this, let me put it over here, let me delete this cell. So now we have read the file, we have found out the mean velocity. Alright, so let me allot it to velo. Alright, now let us also have the standard deviation. So std is equal to np.std of this same thing. So it will give us the standard deviation as well. Alright, so for this particular file, okay, let's do this. Let us do this particular transect first. This particular transect. So let us fix up a value of x. So we're gonna fix x and vary y. Meaning we're gonna fix the second index. So in this case, we have a bunch of data files with the index 2, and we're gonna vary the first index. So basically, we're gonna loop over that di comma I underscore 2 dot csv and stuff like that. All right. So instead of this, we're gonna write file name, and file name is gonna be d percentage d 2 dot csv, and so this is gonna be the data file, but we have to replace the percentage d over here with, say, let me substitute it with I. Okay, so now we must perform a loop. So for I in, so well, let's see what different values we have. So we have 12 comma 2, so we have 12, then 2 comma 2, 3 comma 2, so 2 comma 2, 3 comma 2, 4, 5, 6, 9 and 12. So let me create an array which contains these values. So let me create an array. So I array is equal to np.array 2, 3, 4, 5, 6, 9, 12. So for I in I array, So then file name will be this. In fact, let me show you whether it's gonna pick up the correct file names. So let me just print file name. Forgot this. All right, great. So we are able to obtain all these file names. So now we're gonna read all those. So let's see if there's an error. There's no error. So we are able to load all the files into a data frame. And yeah, let's. Oops. So we have yeah, there's some mismatch. Okay. So in fact, let us print all this. Print. So let me remove this print file name. So instead, let me print the velocity. Oops. Right. So these are the velocities that we obtain. Great. So we did have another data set 0 comma 2 and 1 comma 2. So let me add those indices over here. All right. So let me run this. So this is the velocity set that we have, and let us add all of this to a variable. Okay. So corresponding to this IA, let me declare some additional arrays. So let me declare velo as an array. So np dot zeros, np dot shape of IA. Let me copy this, paste. So this will be for the standard deviation. Let me make another. This will be for the y locations, because you also want to plot the y locations. So what will be the y location? So like I said, the y locations are actually mm, the index multiplied by 1 foot. So 1 foot is approximately 30 centimeters. So let me do this. So yi is equal to I times 0.3. Actually, I cannot do yi because I will actually have these indices. So what I have to do is I in np dot a range, np dot shape, or np dot size of ia, and this file name has to be then iai. So this will make it loop normally, and this has to be iai. So just think about what I've done. I've not done something very complicated. Instead of using I directly from the array, I'm using I as a loop counter, nothing else. There are multiple ways of getting this done. So don't think this is the only way. Now, because I've defined velo as an array, I can define this and I can define this as well. So let me suppress this printing. Let me run this. Great, there's no error. So now what do we have? We have a bunch of y's and we have the corresponding velocities and standard deviations. So now what we can do is we can plot the error. So we're gonna do plt.plot. In fact, error bar. So we're gonna plot y velo standard deviation. So let's see. Great. So this is what the plot we have. In fact, let me put p plt dot x label. So this will be axial distance from fan in meter. Plt dot y label averaged velocity. in meters per second. All right, that's great. Mm, but because there's a scarcity of data, I have not taken data at a very large number of points. Usually that is the case. You don't have so much resource to do that. So let me interpolate the data so that we can make some kind of a cubic approximation of the data. So we've already done this before. So let me import scipy, or rather from scipy dot interpolate import interp p1d, that is one dimensional interpolation. Let me now define f as inter p1, y velo type equal to, not type, kind equal to cubic, and let me declare another y fine as np dot linspace np dot min y to np dot max y, and let me take 30 points. So basically I'm just taking these discrete points, whatever these points are, 0, 0.3 and so on. I'm creating a new array which has more number of points in them. So yf is this, yf stands for y fine. So on top of this I'm gonna plot plt dot plot yf f of yf, and let me put it at a dotted line of black color. So let me plot this. This should be inter p1d. Okay, there's still an error. Inter p1d. I have not yet run this cell. It's a classic mistake. Alright, so this is how the velocity looks like once it is interpolated. You can do various kinds of interpolations, linear, this is a linear interpolation, and you can choose large number of points. Okay, it looks something like this. So great. So far we have done this transect, and similarly you can do this transect as well. So let us see how that can be done. So what are the points that we have? If I remember correctly, for the far transect I did take some points. This 90929496. All right, so the first index is fixed, meaning y is fixed and x is varying. Okay, so the first index is fixed, meaning this y is fixed, the row number is fixed. So what I'm going to do is modify this so that it contains 0, 2, 4 and 6, and modify this so that it is 9 dash percentage d, and in fact it is very easy to reuse that above code. Instead of the label being actual distance, we will say um, not lateral. So we're gonna say transverse distance from axis. And in fact, when we do the transverse distance from the axis, we are gonna take y minus mean of y, so that we can show that the y equal to 0 has the maximum value. And similarly we're gonna do minus np dot mean of yf. Alright, so once I do this, actually I have to feed so yf can remain as it is. We can simply modify this. Okay. mm, at 2.7 meter, because it's all done at a y location of 9, other the row number 9, so 9 corresponds to a distance of 9 times zero point 0.3, which is 2.7. So let me run this. There's an error. Let's see. Okay. Okay. So the interpolation goes out of bound. Mm, because we did an interpolation over here. Hmm. So in fact, let me keep things as they are. And I mean, it's not that difficult to figure out at all. But yeah, I mean, you can try to do, you know what I intended to do, so you can try to do it. We can plot the shifted plots. Plotting it should not be an issue. Let's see. Ah, great. So what do we see? So we do see a maxima somewhere near the origin. There's a big error bar over here. That could be to less number of points. So this would be 9 comma 3. Let's open up 9 4. Okay, so there's data variation from zero point 0.6 all the way to 2.4, so there does seem to be some error. Ideally I would have taken a lot of points and then done the averaging, so that would have led to smaller error bars. That's okay. Okay, so far we have seen how to do all this, but we have a bunch of files, and the indexing of the files does indicate the x and y of that particular data. So there has to be some way of easily extracting the x and y from the file name itself, looping over all the CSV files, and then making a two-dimensional plot of the velocity field. Given that we have only a velocity field at a few scattered points, but still it should be possible. So let's see how we can get that done. So first of all, in order to list all the files in this folder, we must import glob. Okay, so let me run this. So let us check the number of files. So number of files is equal to np.size of glob star.csv. Let me print the number of files. So it says 16. So it's one. So let me see whether they are indeed 16. They are 16. Okay. So we have 16 files of the kind CSV. And this is how you can get all the files. So let me remove this. Okay. So what do we do with this? Okay. So for file name in glob star.csv, print file name. So it prints out all the CSV files. Okay, so this is also good. We can move this to the main cell. Let me delete this. Alright, so now we have a way of sort of printing out the file name. We need to extract those two digits from the file name. So for this, we will utilize what is called as a regular expression or regex functionality of Python. Actually, it is a functionality of Unix. So we will import regex regular expression, and what this will help us is, it will help us to identify strings inside files. So once you see what it is, you will understand what it really means. So matches is equal to ra dot match. Now we're gonna pass the raw string that we want to check, and the raw string that we want to check is d. Then we want to, okay, let me just do this, not csv dot star. dot star, and we will check for this kind of string in file name, and we will have no flags. Okay, so let me print matches. So what I'm doing is I'm taking this raw string, I'm taking the file name, and I'm comparing the file name to this raw string. So dot star means whatever comes in between d dash something and dash, then whatever appears in this placeholder. Okay, so in this placeholder you will have 0 and 2. So let me do this. Print matches 0, print matches 1. Not 0, but this will be, so 0 will give me all the string. So 1 comma 2. So it's matches dot group 1 and group 2. So this actually gives me all the different strings. And if you're not convinced whether this is working or not, let me do this. Number is required. Right. So look, it's giving us all the strings we want, and I've typecasted the string to an integer. And that's standard. I mean, because it's giving you a string output, the matches is giving you a string output. You must typecast it to integer if you want to use it in further calculation. So good. So group 1 is going to be the y coordinate and group 2 is going to be the x coordinate. As simple as that. So x log will be group 2 or match dot group 2 times 0.3. Actually I have to typecast it to float, so I will typecast it to float multiplied by this. Y logs will be float of match dot group 1 times 0.3 match dot matches. Okay, so everything runs fine, and now that we have the file name we can simply reuse all this. So we're gonna copy this bit of code, we're gonna import it, paste it over here. So file name velo y, we don't need y anymore. Actually we do need y, because yi will be y logs, and actually let me write it as points I comma 0 is equal to x logs, and points I comma 1 equal to y logs. Okay, so once we are going in this loop it will take x logs, it will put in points 0 comma 1. So we need to define what points is. So because number of files is 16, so points will be np dot zeros, we're gonna initialize it, and it will be np dot, so it will be actually num files comma 2. So number of rows will be the number of files and 2 columns for x location and y location. Alright, corresponding to these points we will have the velo is equal to np dot zeros num files. So we are soft coding everything. We can put np dot 016, but we are soft coding everything. We don't need the standard deviation in this one, that's fine. So let me run this to see if there's an error. There's no error, great. Let me print what points is. Okay, it does. Hmm. So I have to set I equal to 0 over here. At the end of it, I have to do I equal to I plus 1. Let me run this. Let me run this. Great. We have all the pairs of points. So now that we have all the pairs of points, we must do a two-dimensional interpolation. Okay. So let's get to that. So first of all, we must import grid data. So from scip.interpolate import grid data. So what grid data does is, if you have xy value triplets all over domain, if it's scattered, you can take those scattered points and you can sort of interpolate them over a grid data using this particular function. It will be clear what it means. So let me write x grid is equal to np dot linspace min of mm, points all rows 0th column to max of points all rows 0th column. Similarly, I will define yg as np.linspace min of all rows first column and max of all rows first column. So 0th column are all the x values, the minimum of all the x values and the maximum of all the x values will be sort of used to create the finer grid. And by default it is 50. So this should be np.min and this should be np.max. Similarly, this should be np.max and this should be np.min. Okay. Now with the help of these two axes, we're going to create the mesh. So xg yg is equal to np.mesh grid xg yg. As simple as that. Now once we have this, values on this fine grid will be grid data. So the points pair the values. So the values are velo. Then the xg and yg on which you want to obtain the interpolated values, and finally the method. So the method has to be, there's a bunch of methods we can use: linear, nearest, or cubic. Let's keep it cubic for now. So let me run this and see if there's an error. There's no error. So lastly what we can do is plt.pcolor xg yg vg. So let's see what we obtain. We obtain the interpolated data wherever it's white, meaning it cannot interpolate because we don't have enough points from which we can create that interpolation. So this is great. Let me add a color bar, plt.color bar. Alright, so the velocity is higher near the fan. So this is the location of the fan and it sort of decays. So this is the region. If you sit near this region, you get the maximum wind. If you sit near the edges, you get nothing. Okay. In fact, the interpolation predicts a negative velocity. In fact, let me make this linear. Let's see. Yeah, the linear gets rid of those negative values because the cubic is going to undershoot. The cubic usually does this undershooting business. That's okay because the number of grid points that we had were quite less, right? So just like that, we were able to make a function, a file through which we were able to take data, analyze it, make the 2D map of the data, and I hope you will find this very useful in your endeavors. So with this, we come to the conclusion of this course. I hope you've learned a lot of new things, and hopefully it will benefit you in your research or in your assignments, or in fact your learning as well. I have enjoyed this journey and I really hope you've enjoyed this as well. With this, I sign out. and I'll see you again someday with a new course. Bye.